In this section, we'll discuss electrolysis and other processes that occur when electrochemical reactions happen. We've been studying to this point Voltaic cells, which work as a result of a spontaneous reaction, but we can also use energy from an outside source to make a non-spontaneous reaction take place. Driving a chemical reaction by using outside electric energy is called electrolysis. A cell in which this occurs is called an electrolytic cell. Also, applying a reverse voltage to a voltaic cell can recharge it by running the spontaneous reaction backwards, replenishing the electrodes and ions. In electrolysis, or when recharging a battery, an external voltage that's larger than the cell potential is applied in the opposite direction from that of the voltaic cell. That drives the reaction in the non-spontaneous direction. By definition, the electrode at which oxidation occurs is always called the anode, and the electrode at which reduction takes place is always called the cathode. The external voltage will reverse which electrode is which, since the reaction goes in the opposite direction. And the sign of the voltage will be reversed since the external voltage supply determines that. So in electrolysis, the anode is positive and the cathode is negative, the reverse of what we see in a voltaic cell. So on the left, we have the spontaneous oxidation reduction happening, and we have a electrochemical cell potential of 1.10 volts. And we see electrons flowing from the zinc to the copper. Okay. And so this is where oxidation is occurring. So this is the anode, and then this is the cathode. Electrons flow from anode to cathode, right? Whereas on the right, we have the reverse happening, the electrolytic process, and you can see we have some power source that's much greater than greater than the 1.10 volts, and we force the reaction to go in the opposite direction. So now this would be the anode, and this would be the cathode. So they're switched in an electrolytic process. Okay, some comparisons and some contrasting between the two types of cells. In the electrolytic cell, external energy drives a non-spontaneous reaction. So we need energy from an outside source. Whereas in a voltaic cell, the energy is released from a spontaneous redox reaction. In that case, the system then would do work on the surroundings as that energy is released. Whereas in the electrolytic cell, the surroundings have to provide that energy or do work on the system. In the voltaic cell, the anode is at the positive voltage and the cathode is at the negative voltage. The reverse is true for the electrolytic cell. The anode, though, is always where oxidation occurs, and the cathode is always where reduction occurs. So the anode for a voltaic cell becomes the cathode for the electrolytic cell, and vice versa. One use for these electrolytic reactions is in electroplating. Electroplating uses an active electrode to deposit a thin layer of one metal to another metal object. The item that is being coated with the metal is the cathode, and those metal ions are being reduced at the anode. So I have a silver cathode here, okay, and as my electrons flow, I have metal plating happening of the silver metal. One of the things we're often asked to do is determine how much the mass of an electrode changes, either increases or decreases, in a voltaic or electrolytic cell. Here's how we do that. First, measure the electric current and the time it has been running. Then, determine the charge transferred, how much charge is transferred, using the relationship that 1 amp of current represents 1 coulomb per second. So the total amount of charge is the current multiplied by the time interval. Convert from charge to the number of moles of electrons using the Faraday constant, which is 96,500 coulombs per mole. Okay, coulombs per mole, so we can convert to moles. Then use the formula for the reaction to determine the ratio of the moles of electrons to the moles of the species of interest, whether we're talking about the cathode or the anode mass, and then use the periodic table to determine the mass of that many moles of those atoms or molecules. So let's walk through an electrolysis practice problem. A 7 amp current passes through molten aluminum chloride in an electrolytic cell for 60 minutes. What mass of aluminum will be deposited? So we start here with the formula for what's happening, okay, where we're depositing the aluminum. So that's our solid, okay, aluminum solid. The current is 70 amps. The time in 60 minutes is 3,600 seconds. So we can find Q. Q is 25,200 coulombs. Once we know the charge, we can find the number of moles of electrons using the Faraday constant. So 25,200 coulombs divided by 96,500 coulombs per mole of electron is 0.261 moles of electrons. Now, we use the stoichiometry of this formula at the top to say that the moles of electrons, or the moles of aluminum, are equal to the moles of electrons divided by 3, because there's 3 times as many electrons consumed, moles consumed, as there are aluminum moles produced. Okay, so we have a mole ratio that says 3 moles of electrons for every 1 mole of aluminum. Okay, so we find our moles of aluminum there just using the stoichiometry. We get 0.087 moles of aluminum, and we can convert that to grams using the molar mass of aluminum, 2.35 grams. That's what mass of aluminum we would expect after 60 minutes of current passes through the electrolytic cell. All right, here's a second practice problem. A 2.00 amp current is generated by a copper zinc voltaic cell. How much will the mass of the zinc electrode be reduced in 15 minutes? So we start with our formula for, this is the reduction of zinc. We know that zinc is being oxidized, though, if the zinc solid is decreasing in mass. It's not being produced. It's being used up through the release of those 2 electrons. So let's start with our current, 2 amps multiplied by 900 seconds. 15 minutes is 900 seconds. We get 1,800 coulombs of charge. We need to convert that charge into moles of electrons using Faraday's constant. So we divide by Faraday's constant to get 0.0186 moles of electrons. Then we need to use the stoichiometry here that says twice as many electrons as are consumed as zinc metal is produced, or the other way around, half as much zinc metal is produced, is consumed as electrons are produced. And so I'm going to divide my moles of electrons by 2, given that stoichiometry, to get 0.00932 moles of zinc. And I can convert that to grams using the molar mass of zinc here. 0.610 grams of zinc should leave the zinc electrode in its oxidation in a time of 15 minutes. We can also figure out how long the current has been flowing if we're given the change in mass, essentially by just working backwards. So given the change in mass in the electric current, we can just reverse our sequence of steps to find the elapsed time. So use the periodic table to determine the number of moles of that mass of atoms or molecules. Use the formula for the reaction to find the ratio of the moles of electrons to the moles of that atom or molecule. Convert to charge, and then use the given current to find the time. How many minutes will it take to plate out 6.36 grams of copper metal from a solution of copper 2+ using a current of 12 amps in an electrolytic cell? So here's the half reaction for the plating of the copper. Okay. Start by finding the moles of copper, which is the mass of the copper, divided by the molar mass. So 6.36 over 63.5 grams per mole is 0.1 moles. And you can see that there are 2 moles of electrons per mole of copper. So if I have 0.1 moles of copper, I need to just double it to find the number of moles of electrons. Then Q, the charge, is equal to the moles of electrons times Faraday's constant, 19,300 coulombs. And then the time is related to the current. It's the charge over the current, 19,300 coulombs over 12 amps is 1,608 seconds or 26.8 minutes.